Okay, so now we're going to look at another histogram. I have some data here. What I did is I just rounded the data on the sheet, so I didn't have to copy it all, but the histogram's going to come out more or less the same. We'll find here we have some issues. The issues are, what do we do with values that appear on the border? So maybe we don't have any. Let me see. Oh, here's a 9. So this 9, you see, it is in both categories here. So we'd have to decide which bin to put the 9 in. Maybe there's some other stuff like it out there. Do you see anything else? I'm looking. 6, 7, 4, 10.5 maybe? Or is it just the 1, 9? Oh, here's a 10.5. Another problem. It's here and it's here. So what you do is you just make a consistent choice of where you're going to put that number. And the way you indicate that, at least the way I'm going to do it here, so I'm going to put a little minus sign here, saying this is 4.5 up to 60, but not quite including 60. Everything less than 6, but not quite 6. Less than 7.5, less than 9.0, less than 10, less than 12, like that. So the bar indicates, and the bar indicates, yeah, I'm making sure I can see it. Up to, but not including. Okay, we're just about out of space, but we're okay. So we're going to all the way up to 6, but not 6. So here we go. 4.5 is one of them. 4.9. Maybe we should change colors. Looking for 4.5 up to 6. Looks like there's 4 there, and then 6 to 7.5. 1. There's a 6 there. Oh, 2. 6 included. 6 is not in there. Okay. 6 up to 7.5. 3. 7.5. 6 to 7.5. Step back for a second. Did I get them all? That's really a 6. 6 up to 7.5. Let's see. No, that one was 4.5 up to 6. 6 up to 7.5. Okay. 1, 2, 3, 4. Looks like 5. And then 7.5 up to 9, but not 9. 1, 2, 7.5 up. Okay, 3, 7.5 up to 9, but not including 9. What about the 7? He was down here, huh? Make a dot on him. Okay. Where was I? I was 7.5 up to 9. Little X's. Okay. But I ran across the new guy. 7.5 up to 9. So that's one of them there. 7.5. I think I got them all. I'm not convinced though. So little X's are 7.5 up to 9. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, maybe. Oh, but not including 9. So this guy was, I had him marked because he's an outline. He's the one that I have to worry about. Okay. 5.6. Why is 5.6 marked? I'm crossing my fingers. So hang on. So 7.5 up to 9. This is the X's. The 4 up to 6. Oh, that's these. Okay. That's this. And 6 up to 7.5, that's the dots, okay. Now we're doing 9 to 10.5. I'm going to use check marks now. 9 to 10.5. 1, 2, to use 10.5? No. This one's in though. Okay. Is there anything left? Just the 10.5 it looks like. Oh, there's 11.5 there. I guess he's in there too, huh? I'll go to count my check marks in a minute. Everything been marked? Looks like it has. Looking for check marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think we might have accomplished the task. If I want to be really serious about it, there's supposed to be 30 values. I don't see 30 check marks. I'm missing one. Oh my. Okay, so first make sure everything's marked. Okay, so the underlines, double underlines. 1, 2, 3, 4. So we got that. 6 to 7, the dots. 1, 2, 3, 4, 5 dots. It says 6. Come here. 1, 2, 3, 4. I only get 5. Maybe. I'm still concerned now. Everything's marked, so this should work. If we just get them all, we should be fine. So I've got 2 stars. Okay. I got check marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 11. Heavens. All right. I have to count more carefully. Double bars. 1, 2, 3, 4, 5. Okay. Single dots. 1, 2, 3, 4, 5, 6. Guess we were right before. Crosses. 1, 2, crosses. 2, 3, 4, 5, 6. Sorry about the effort. I think we did it. 6, that looks all right. And then the check marks. 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11. And then this is 2. So now I've got 5 left over. 10, 20, 30. We're in business. Okay. The double check worked, but it took a lot of effort. Drawing the graph should be easy. The height here should be up to 11. Okay. Then we're going to go height 5. Did it? Height 6. Height 6. Height 11. And height 2. Did it? Yeah. All right. And next on our list of things to do is to talk about shapes of distributions. The first situation is to talk about symmetry and skewed. So for a symmetry, more or less, you just you draw the picture like that and you go to the middle. Somehow the middle is obvious to people looking at it. And you imagine folding this over and seeing if the one side lines up with the other side. So it's a natural notion of symmetry where the two sides are identical, one's just a mirror image. So you can imagine putting a mirror here and reflecting it around. So a mirror image. Now you have a little bit of flexibility. We usually say approximately symmetric. Usually only approximate. So with approximate symmetry, you know, well, maybe this is only approximate, so this doesn't match that exactly, but it's more or less symmetric. And for skewed, we don't have that situation. There's no way to line things up. Well, this is pretty close. For skewed distributions, you have this kind of lack of symmetry that's consistent. And it's a little bit difficult to decide how to describe that, but one way to do it is like this. You draw a line here where it's equal areas. So that's a little bit difficult to do. I'll try to do it with these. So maybe it's here. Maybe I should use a different color. The equal areas on each side. It's a little hard to do if you're not used to looking at areas. So this one extends over here a little bit. So if I cut it here, there's too much area on that side. I'll have to cut it a little bit like that, I suppose. Hard to tell. Equal areas. Maybe here. Oh my. Maybe here. And then maybe there, like that. And then we look to see how far the values extend on each side. If those distances aren't the same, then we say the distribution is skewed. And we say it's skewed in the direction where it extends further. So all of this is left, since that's longer. This is skewed right. This is skewed left. Somewhat skewed. Somewhat skewed left. And this is right. Skewed right. Skewed right. And skewed left. And that type of thinking works with histograms, dot plots, and stem and leaf. All you have to do is lay everything down in this on the ground like this, so you have a number line here. Ordinarily you make stem and leaves with the number line vertically. You might not have noticed that, but then if you turn it this way, it turns into a number line. That's why we start with the smaller numbers on top and the larger numbers on the bottom, so we can then go like this, and it matches the shape and display that a histogram has, where the number line is going in the usual direction, increasing numbers to the right. So now we can talk about symmetric and skewed distributions. Of course, it's not a complete description of shape. Really weird things can happen when you collect data. But if you collect a sufficient amount of information, usually some of these shapes will start to take form. And you say, well, I bet you if I collected more information, that shape would continue. And when you're in that situation, it makes sense to say, it looks like this data came from a population that's also probably skewed or approximately symmetric. Once you see enough of the information from the population, a large enough sample, you can draw conclusions about the shape of the population distribution. That would be what you would get if you made a histogram of all the values present in the population. So there we go. Dealing with values that appear on the boundary of the bins in a consistent way by saying we'll go up to but not including by this little minus sign, and then talking about symmetry and skew distributions based on the shape of the graphs. The graphs are histograms, stem and leaf, or dot plots. They all have the same basic characteristics. If the values are symmetric, if the data is considered symmetric, any stem and leaf or a dot plot or a histogram will all have this kind of symmetry to it. And if the data is skewed, the stem and leaf, the dot plot, the histogram will all have this kind of shape where there's more values on one end than the other, and there's no symmetry to it. And if you find the center value, divide the number of values approximately in half, you go further one way than the other to get to the extremes. And that longer distance is the direction that the distribution is said to be skewed to. Longer on the left, skewed left. Longer on the right, skewed right. Okay, we did that. There's still more to go in this section, so I'm hanging up my slide. I think I'm out of rags to clean off the board, and I'll just have to go home and do my laundry.